using matrix vector product. Case of DFT analysis equation, which can be written in the form of matrices like this one, we have to multiply a time domain sequence, which is a one-dimensional vector, with the W4 matrix because the value of n is 4. So the idea is the values of W4 matrix are pre-calculated, or practically they are pre-stored in our computer memory, and we are just going to multiply this W4 matrix with the incoming time domain sequence, which also contains 4 samples. So when we will multiply first row of this W4 matrix with the time domain sequence, we will get the DC coefficient value. On multiplying the second row of this W4 matrix with the same time domain sequence, we will get the result of fundamental harmonic contribution. Similarly, when we will multiply the third row of this W4 matrix with the time domain sequence, we will get the result of x of 2. And similarly, x of 3 can be calculated in a very similar way. So just multiply all 4 rows of a W4 matrix with this time domain sequence. Here we have replaced the values of time domain sequence by its sample values. So x of 0, x of 1, x of 2 and x of 3 are replaced by 1, 1, 0, 0. So now just multiply this W4 matrix with this one-dimensional vector. On multiplying a W4 matrix with the time domain vector, we will get these results, which can be further simplified, and the final result will be equal to x of k is 2, 1 minus j, 0, 1 plus j. So this is the frequency domain vector or DFT coefficients which we obtained previously when we calculated DFT equation in its standard format. Now let's come to example 3, in which it is required to find or recover x of n with the help of these DFT coefficients. So this is the case of inverse DFT, which can be solved using DFT synthesis equation in the form of matrices. Now, as we discussed earlier, there are two possible methods to solve the synthesis equation of DFT in the form of matrices. The first method involves inverse of a W matrix, while the second method includes conjugate of the same W matrix and then divided by n. So we are going to use the second method, in which we will take the conjugate of the W4 matrix and then we will multiply it with the frequency domain vector, and finally we will divide it by 4. So now replace the values of x of 0, x of 1, x of 2 and x of 3 by the given DFT coefficients. So these are the DFT coefficients which were given to us, and now we are going to take the conjugate of this W4 matrix. While taking conjugate of the W4 matrix, you must remember that we have to just flip the sign of imaginary terms, not the real terms. So the real numbers, which are 1 and minus 1, will remain same or as it is after taking conjugate, while the imaginary terms, which are minus j and plus j, will become plus j and minus j. So this minus j and minus j is replaced by plus j, and this plus j and this plus j will become minus j and minus j. Now, after taking the conjugate of the W4 matrix, we have to multiply this matrix with this vector. After multiplying the conjugate of a W matrix with a frequency domain vector, we will get these numbers, which can be then simplified to 4, 4, 0, 0. You can solve them mathematically. And after dividing these values 4, 4, 0, 0 by 4, we will get the result 1, 1, 0, 0, which is the time domain sequence. So as you can see, we got the same time domain sample values which were provided in numerical number 2. So this is how we can calculate the inverse DFT by using matrices, in which we just need to calculate the conjugate of the W and matrix. So it's much easier to calculate the synthesis equation of DFT rather than solving the inverse of the WN matrix. Now let's conclude this lecture on two important properties of the DFT transformation factors, which are also called Twiddle factors. The first property is periodicity property, which states that Wn k plus n is equal to Wnk, which means after n number of samples, we will get the same Twiddle factors. Or in other words, Twiddle factors will repeat themselves, or the transformation factor values will repeat themselves after n number of samples, where n is representing the length of DFT. While the second property is the symmetry property, which states that Wn k plus n by 2 will be equal to minus times Wnk, which means after n by 2 samples, we will get the same Twiddle factors Wnk, but having an opposite sign. So basically these two Twiddle factors will be 180-degree out of phase with each other. Now, how we can prove these two properties? Let's check them in the upcoming slides. Let's start with the periodicity property, which is Wnk plus n is equal to Wnk. As you already know, mathematically Wn is equal to exponential minus j 2 pi over n. So what we can do here, we can simply replace Wn by exponential minus j 2 pi over n. So Wnk plus n will become equal to this thing, exponential minus j 2 pi over n has replaced the Wn factor, and k plus n, which is written in the superscript of this Wn factor, will become the power of this complex exponential. So these two powers can be multiplied with each other, so you will get this term. Now you can separate the two factors which are present in the complex exponential. The first factor is exponential minus j 2 pi k over capital N, and the second factor is exponential minus j 2 pi capital N divided by capital N. So these two n's will cancel out each other, and we will simply get exponential minus j 2 pi. Now exponential minus j 2 pi will be equal to cos 2 pi minus j sin 2 pi, and we already know cos 2 pi is equal to 1 and sin 2 pi is equal to 0. So this factor is simply equal to 1, which will be multiplied with exponential minus j 2 pi k over n. Now if we will write this complex exponential in the form of Wn notation, how we can write it? This exponential minus j 2 pi over n can simply be written as Wn, while this k, which is written with a red color, can be considered as the power of this complex exponential, which can be written in the superscript of this Wn notation. So the final observation is Wnk plus n is simply equal to Wnk, which shows that after n sample interval, we will get the same Twiddle factors. Now, in order to observe how this relation is actually working, we can assume some values. So we are going to assume capital N is equal to 4, and we are changing the values of k from 0 to 3. On substituting the values of n is equal to 4 and k is equal to 0, 1, 2, 3 in this relation, we will get these results. So W4 4 will be equal to W4 0. So W4 4 will not be a new factor or a new number, it will be exactly equal to the W4 0. Similarly, W4 5 will be equal to W4 1, W4 6 will be equal to W4 2, and W4 7 will be equal to W4 3. Now let's come to the symmetry property, and we can also prove this property in a very similar way. We can replace Wn by exponential minus j 2 pi over n. So Wnk plus n by 2 can be written like this, where we have replaced Wn by exponential minus j 2 pi over n, while k plus n by 2, which is written in the superscript of Wn notation, will become the power of this complex exponential, and these two powers could be multiplied together. So we will get these two terms in the complex exponential. So the first term is exponential minus j 2 pi k over capital N, and the second term is exponential minus j 2 pi into n over 2 divided by n. On simplifying, we will get the second term as exponential minus j pi. And exponential minus j pi is equal to cos pi minus j sin pi, and cos pi is -1 while sin pi is 0. So this exponential minus j pi can simply be replaced by -1, which will be multiplied with exponential minus j 2 pi k over capital N. Now we are going to write this complex function exponential minus j 2 pi over n in the compact notation, which is the Wn notation. So exponential minus j 2 pi over n will be simply replaced by Wn, while this k will appear in the superscript of this Wn notation. So this is the final observation of symmetry property, which states that after n by 2 sample interval, we will get the originally calculated or previously calculated total factors but having an opposite sign. Now let's assume capital N is equal to 4 and k is equal to 0, 1, 2, 3 in this equation. So we will get these results on substituting these values. W42 will be equal to minus times W40. W43 will be equal to W41 multiplied by -1. W44 will be equal to minus times W42. W45 will be equal to minus times W43. Now, what is the significance or usage of these two properties? On using these two properties, we can complete the transformation matrix directly without solving each and every single entry. So let's see how we can do it. Now let's consider this example where we will try to write the transformation matrix values by using periodicity and symmetry properties. So the idea is in the W4 matrix, we have to just calculate two values, which are W40 and W41. With the help of these two values, we can fill the whole matrix. So there is no need to find the remaining entries in this W4 matrix. And to find the values of W40 and W41, there is no need to use calculator. We can write them directly because W40 will be 1 as we discussed earlier. So the first row and first column will be equal to 1, while W41 will be equal to exponential minus j 2 pi over 4, or simply exponential minus j pi by 2. And exponential minus j pi by 2 is basically cos pi by 2 minus j sin pi by 2. And cos pi by 2 is 0 while sin pi by 2 is 1. So 1 will be multiplied with minus j and we will get minus j for W41. Now we can find all the remaining entries of this matrix by using these two values 1 and minus j by using periodicity and symmetry properties. So let's see how we can do it. Let's start with this factor W44. We have to remember the relation of both periodicity and symmetry properties. In the periodicity property, we have to use a relation of k plus n, while in symmetry property, we have to use a relation of k plus n by 2. And in this example, the value of capital N is equal to 4. So W44 will be exactly equal to W40. Here we have used the periodicity property because 0 plus 4 will be simply 4. So on applying periodicity property, we can write W44 which will be exactly equal to W40. So here we can write 1 because W40 was also equal to 1. Now let's come to these two values W42. By applying symmetry property, we can simply state that W42 will be equal to negative times W40 because k plus n by 2 relation states that 0 plus 4 divided by 2 will be 2. So W42 will be equal to negative times of W40. And what was the value of W40? It was 1. So 1 into minus 1 will be minus 1. So the values of W42 will be equal to minus 1. Here we have applied symmetry property on the W40 factor. Now let's come to W46. By using periodicity property, we can write the values of W46 because 2 plus 4 will be 6. So on applying periodicity property on these two factors, we can simply write the values of W46, which will be exactly equal to the values of W42. So W46 will be replaced by -1. Now let's come to W43. By applying symmetry property on this W41 factor, we can write their values. So W43 will be equal to minus times W41. And what was the value of W41? It was minus j. So minus times minus j will become plus j. And here we have used the relation of 1 plus 4 divided by 2. 4 divided by 2 is 2 and 2 plus 1 is 3. So W43 is simply negative times of W41. Now let's come to the last element of this matrix, which is W49. Here we can use the periodicity property. As you can see, by applying periodicity property on W41, the next factor whose value will be equal to W41 will be the factor W45, which is not available here, but by keeping the idea of periodicity in our mind, we can simply extend that idea up for the next periodic repetition. So W41 will be equal to W45, and on adding 4 into 5 we will get W49. So W41, W45 and W49, all these factors will be equal mathematically. So W49 will be exactly equal to W41. Here we have used the periodicity property on the W41 factor. So this is how we can complete the transformation matrix by using periodicity and symmetry properties. One thing which you should remember, that if you are going to use these two properties in your examination, then you must have to mention those properties, how you have obtained these values. Let's say you have to write W46 will be equal to W42, and you will mention this thing as 2 plus 4 is equal to 6. That's how W46 will be equal to W42. So you have to provide their relations. If you will write the values of transformation matrix directly, then you will simply get 0. And if you are not going to use periodicity and symmetry properties, so the other possible way is you will need to calculate the numeric values of W4 matrix as we did previously. So there are two possible ways to write down the values of transformation matrix. You can choose either of the two possible methods, but you have to mention the steps in both methods. I'm again repeating, if you will write the values of this transformation matrix directly without mentioning any step, then you will simply get 0. That's it. Thank you very much.